Welcome back to the last lecture in Module 2, Mathematical Modeling. In this lecture, we would finish off our unfinished business in governing equations, that is, we would obtain a governing equation for transport of a generalized scalar quantity. Then we would focus on mathematical classification of governing equations in fluid flow and look at what are the initial and boundary conditions we require for numerical solution of the flow problems. Just a brief recap of what we did in last lecture. We derived energy equation starting from the first law of thermodynamics. We obtained the integral form for the total energy, and thereafter we invoked Gauss divergence theorem to obtain the differential form of the total energy equation. From that we subtracted mechanical energy equation and we obtained a thermal energy equation and its different forms. In this lecture we would focus on scalar transport, mathematical classification and boundary conditions which we require in flow problems. So that is what our outline would be. We would start off with a scalar transport equation, obtain an integral equation for transport of a generalized scalar quantity, and thereafter again we would obtain as usual a differential form of transport equation. Then we will have a look at mathematical classification, in particular the classification of quasi-linear PDAs and how we can extend this classification to the flow problems, the governing equation of fluid flow, and in what way do they affect our choice of initial and boundary conditions. And we would also have a look at the classification of Euler and full potential equations, and in the end we will have a brief look at most commonly encountered boundary conditions for flow problems. So let us start off with conservation of a scalar quantity. So we will invoke an analogy of what we saw earlier in the case of energy equation or momentum equation or mass. Okay. So we can extend the same conservation principle, that is to say we want to find out the time rate of increase of a scalar quantity phi in the system. Now this increase could be due to two reasons. The first one is there is some amount of phi which is being transported across the control volume boundaries. Okay. So net rate of increase of phi due to diffusion across the CV boundary plus net rate of creation of phi inside the control volume. To understand this analogy further, let us have a brief look at what we did earlier in the case of energy equation. Let us explore the analogy further and let us go back to the statement of energy equation. So what we had in the case of energy equation, we had rate of change of energy in our control volume. This was contributed by two terms, the diffusion, or in general we can say the transport of energy through the boundary of our problem domain, plus the second one we had was the generation of energy which could be due to a chemical reaction inside the control volume. In fact, we will find similar sort of things happening in the case of momentum equation. So let us also have a look at momentum equation. What we had, the rate of change of momentum dp by dt. Okay. Now this can be caused because of two things. First is we have got a body force which is similar to a source term inside the body. So resultant of body forces So, this body forces sort of represent what we call the sources of, let us say, force present inside the body plus surface forces acting at the boundary. Now, the second part, if you look at the surface forces, this could be thought of as diffusion of momentum, or this happens because of the transport momentum across the control surface. So, this explains the analogy which we had invoked in this case. For a generic scalar, we can say the time rate of increase of a scalar phi is because of two things: net rate of increase of phi due to diffusion across the CV boundary plus net rate of creation of phi inside the control volume. Now, we can invoke the Reynolds transport theorem to convert the rates for a system to that of a control volume. The time rate of increase of a scalar in the system, this is equal to rate of increase of phi inside the control volume plus net rate of decrease of phi due to convection across the CV boundary. So, if we combine these two equations together, on the left hand side we will get rate of increase of phi inside the CV plus net rate of decrease of phi due to convection across CV boundary is equal to net rate of increase of phi due to diffusion across the CV boundary plus net rate of creation of phi inside the control volume. So, let us have a relook. This rate of increase of phi inside the CV, this would be essentially a time derivative of a volume integral, and this convection term, that would be because of a surface integral, the convection of phi because of fluid flow, and RHS again we got increase of phi due to diffusion across CV boundary, this will again be represented by surface integral, and the last term would be due to a volume integral, which is a net sum of the different sources inside the volume. Now, to obtain the formal equation, let us have a detailed look at each one of these terms. So, on the left hand side we have the term that is rate of increase of phi, sorry, scalar transport time rate of increase of phi inside the CV. Now, this is simply the temporal derivative of rho small phi. Here we have assumed this phi is an intrinsic quantity. So, essentially this phi represents a physical quantity per unit mass d omega, and convection of phi through control surfaces this would be given by a surface integral across our control surface rho phi v dot dA. Next, let us talk about the terms which contribute to it, or the interactions from the sources and the transport of phi across the boundary. The first one is rate of generation of phi, inside CV. This can be expressed as a volume integral of q subscript phi dot d omega. Now, here similar to what we saw in the case of our energy equation, this q dot phi, this represents the source term we can call it as volumetric generation rate, and the last term which we had, that is diffusion of phi through control surface now this we can represent by a simply by surface integral of a flux like quantity. Let us say that q is the flux of phi which is being transported across the control surface. So, q dot dA integrated over our surface, that will give us the efflux or net rate of efflux of q across the control volume surfaces. So, now we can substitute these 4 integrals which we obtained in our verbal equation which we derived earlier, and that leads to the integral form of the scalar transport equation. So, this is the form of conservation equation for a generic scalar quantity. So, we can also call it generic transport equation del phi say del by del t of rho phi d omega plus phi times rho v dot dA is equal to surface integral of gamma times gradient of phi dot dA. Now, this gamma times gradient of phi we have put here, assuming that this is a this q can be represented in terms of a diffusion coefficient gamma and gradient of a scalar quantity phi. So, gamma gradient of phi dot dA plus rho times q phi d omega. Now, let us obtain the differential form of the generic transport equation. Now, this we can again do by following the same method which we had adopted earlier for derivation of the differential forms, starting from the integral forms. So, differential form of generic transport equation. So, let us first write down our integral form. We had first one was a time derivative del by del t of rho phi d omega. Now, for a fixed control mass or fixed mass, we can represent it as an integral of the time derivative, that is del of rho phi over del t d omega. The second term which we had on the left hand side of our integral form, that was a surface integral, that was rho phi v dot dA, which represents the convection of phi across the control surface. Now, this can be changed using Gauss divergence theorem. Into a volume integral. So, this is divergence of rho phi v d omega. Similarly, we had a surface integral on the right hand side, which was because of the flux term. So, S q dot dA, this can be transformed into a volume integral divergence of q d omega. So, now let us combine these all these terms together and transfer everything on the left hand side. So, we have a big volume integral del of rho phi over del t plus divergence of rho phi v minus divergence of q minus q phi dot d omega, this is equal to 0. So, once again we get an integral which is 0, and this integral will be 0 irrespective of our chosen control volume omega. Okay. So, this usual argument again applies. It holds if and only if the integrand vanishes everywhere, in omega. That is, our time derivative of rho phi plus divergence of rho phi into V minus divergence of q minus q dot phi, this is equal to 0. So, now let us keep our unknown term on the left hand side, transfer rest on the right hand side by slight rearrangement. So, del by del t of rho phi plus divergence of rho phi v is equal to divergence of q plus q dot phi. So, this is our differential form. This is differential form of generic transport equation. It is not too difficult to realize that, look, this equation can represent any of the few equations which we have derived earlier. For instance, if we replace phi by 1, what do we get? So, let us just do for sake of exercise that this generic form which we have derived, does it or can it be made to represent a few transport equations which we have derived earlier? Generic transport equation let us rewrite it again. So, del by del t of rho phi plus divergence of rho phi v divergence of q plus q dot phi. We can call it a generic transport equation only if it can be used for different conserved quantities. So, suppose we take phi is equal to 1. Suppose we take phi is equal to 1. What does that mean? That is, the transported quantity capital phi, that must be mass. So, if you substitute phi is equal to 1 in the previous equation, what do we get? We get del rho by del t plus divergence of rho v, and in this case, if you are dealing with the mass of a system, there is no diffusion of mass through the control surface, nor is any mass source inside. So, the right hand side must be 0. So, what we have got? This is precisely the continuity equation which we have derived earlier. Similarly, for phi we can substitute. Similarly, we can substitute for small phi any velocity component, and this will lead us to an appropriate form for momentum equation. Of course, we will have to interpret the fluxes in that case. Our q would be given in terms of stress components or the derivative stress of divergence of stress, and q phi that would be given in terms of the body forces. and if we take phi is equal to small e, eta or small e, now our generic equation, the generic transport equation would lead us to energy equation. So that's what we see, that the so called this generalized transport equation which we have derived, that can be made to represent the transport of any conserved quantity. So in the remainder of the course, in fact the first half of the course of the CFD, we would primarily focus on our attention on finding out or deriving the numerical schemes which can solve this generic transport equation, and only thereafter we would apply those techniques, or we will extend those techniques for the solution of full Navier-Stokes equations. Now before we can proceed with the numerical solution, we have to grapple with few issues, that what should our choice of the governing equations be. That is one thing that will depend on the physical phenomena, and based on the physical phenomena, physical situations, we can derive the way we have learnt our governing equations, that is the basic conservation laws which will give us the equations for continuity, momentum and energy. But we should know what is the nature of these equations, because that will dictate the choice of the numerical schemes which we can use. So if you look at any of the equations, our governing equations of fluid flow, these are second order non-linear partial differential equations in 4 independent variables. For time dependent problems, time is 1 and 3 space coordinates. So mathematical classification of these non-linear PDEs is a rather difficult task, but we have to get some picture, at least some qualitative picture, because choice of numerical scheme as well as the number of initial and boundary conditions which you will require, that depends on the mathematical nature of our governing equations. So we have got no option but to explore, or at least get some estimate before we can proceed with the choice of the numerical schemes. So what we normally do is that we attempt a classification of our governing equation, that is our Navier-Stokes equations and energy equations, usually based on their linearized form. So our first task would be to have a look at the classification of this linear or quasi-linear second order partial differential equations. So now let us have a look at a generic or generalized quasi-linear partial differential equation, which we can represent in this form. Suppose for the time being we are dealing with an unknown function or unknown variable u, which is dependent on 2 variables x and y. So for this situation we can write our generic second order PD as a times del 2 u over del x square plus b times del 2 u by del x del y plus c times del 2 u by del y square plus d times del u by del x plus e times del u by del y plus f times u plus g is equal to 0. Now here a, b, c, d, e, f and g, these would in general be functions of x and y. Now what would be the nature of this particular equation? We can derive the so called equations for characteristics for this case, and those characteristics are basically given by the discriminant, so called discriminant b square minus 4ac. Okay. Now this particular term b square minus 4ac, in fact it comes if we compare this equation with the second order algebraic equation. So let us have a detour and let us have a look at our second order algebraic equation. In 2 variables. So we can write this as a x square plus b times xy plus c times y square plus dx plus Ey plus f is equal to 0. If you recall from geometry, this second order equation represents an equation of a conic section. So, it represents a conic section. By conic section we mean here it could be a circle, it could be a parabola or ellipse or a hyperbola. So, what are the conditions for each type of conic section? So, what we will see that would depend on the discriminant b square minus 4 ac. So, we say that if b square minus 4 ac this is greater than 0, then this equation represents a hyperbola. Hyperbola is essentially a curve, in fact it contains two different curves, a combination of two curves, b square minus 4 ac equal to 0. So, in this case we have got a single characteristic and we call this curve as parabola, and b square minus 4 ac is less than 0, we do not get any characteristics and we call this equation as, or rather this equation represents our geometric shape called ellipse. Circle of course is a specialized case of an ellipse. So, our classification for PD is basically, or the nomenclature which we use, that follows our nomenclature used in geometry for classification of hyperbola, parabola and ellipse. Let us have a look at discriminant b square minus 4 ac. Now, if it is greater than 0, we have got two real characteristics. The characteristic are the ones basically the space curves along which information would propagate. So, b square minus 4 ac being greater than 0, that says that we will have two real characteristics, and in this case our equation or PDE would have what we call hyperbolic nature, because that is what we have got. In the case of hyperbola we have got two different or two distinct branches of an hyperbola. So, it is the same analogy which is being used in this classification. B square minus 4 AC is equal to 0. So, we have got one real characteristic, that is we have got only a single branch in the case of parabola, and the same terminology we use here, that b square minus 4 AC is equal to 0. This equation would be called parabolic. And a b square minus 4 AC is less than 0, we have got no real characteristics, and in that case we will term our quasi-linear PDE as elliptic. Now, let us have a look at one example of each of these types of equations and what do these mean. So, let us have a look at a hyperbolic equation. Now, in the case of hyperbolic PDE, we have got two distinct characteristics. Okay, and the information, that is to say, if you have got a problem domain, we introduce at some point some disturbance. That disturbance propagates along these characteristic lines. There are characteristic lines along which the information propagates, and the information propagates at a finite speed. So, we have got finite speed of propagation of information regarding where that particular disturbance was introduced and what is its effect on the field. So, a typical example of this equation would be a wave equation. A typical example of hyperbolic PD is del 2 u over del t square is equal to c square del 2 u over del x squared. Let us see what this geometrically means. We have got two independent variables here, x and t, and suppose we say that extent of our physical domain in x is along a and b. So, our information would propagate, or if you look at any particular point p where we want to see what would happen at a given instant of time, the things at p would be influenced by the information contained in this region, the characteristics which are propagating through p originating from either side. Okay. So, what we would say that this particular slant hatched domain is what we call is domain of dependence. So, solution at point p that depends on only this slant hatched portion, and whatever happens at point p that affects only this narrow region contained between these characteristics. Let me put these as horizontally hatched region. So, this region we would call as domain of influence. That simply means if you introduce a disturbance at point p, that will affect the solution only in this small region of space and time. This at any point, let us say if you have got a point q located here, anything happening at p will not affect what happens at q. So, that is the basic nature of the hyperbolic PD, is that the domain of dependence and domain of influence are both fairly confined or well defined regions in space, and in this case we will typically need, this is second order PD in time. So, we will need two initial conditions and two boundary conditions given at points a and b. Next, let us have a look at the next type, that is a parabolic equation. Now, in this case of parabolic equation we have got only one real characteristic, and it says that information would propagate along only one direction. For instance, if we have a time dependent problem, suppose one dimension in space and one dimension in time. So, now in this case whatever has happened in our domain or physical problem domain at time prior to a time t1, that will affect our solution at point x t1. So, whatever happens before p in terms of time, that will affect the solution at p. Similarly, the happenings at point p, they will affect only the solution behavior only at future times, not at the prior times. So, now in this case this becomes sort of what we call our domain of dependence, and on the later times, or what we can say, this is domain of influence. So, the beautiful thing about this parabolic PD is that information propagation, the information propagates only in one direction, and this simplifies your task quite a bit, that we can do what we can say marching or we can apply marching type numerical schemes. That is, if we have got a time t is equal to 0, we know what the solutions at different points are. Using these solutions we obtain, or we can obtain a solution at a time slightly afterwards. Let us say at time t is equal to delta t. Now we can use the solutions at these values and obtain the solution at t is equal to 2 delta t and so on, and thereby we can just keep marching along the time direction. So the solution procedure is fairly simple in the case of parabolic equation. And a typical example of such equations is our heat conduction equation. Heat conduction, or we can also call it heat diffusion equation. So if in 1D we can write it as del U by del T is equal to alpha times del square U. This alpha represents our thermal diffusivity. Now let us have a look at carefully here. Now this first order derivative is involved in time. Derivative in time, and on the right hand side what we have got, if you look at the expanded form of our del square operator, this is del 2 by del x square plus del 2 by del y square, and this operator we would see it has got a so called elliptic nature. So in fact some people call this heat diffusion equation as parabolic in time and elliptic in space. Now the last type which we discussed, this elliptic equations. A typical example is our steady state heat conduction equation del square T is equal to 0. Now in such cases, suppose we have got a domain, problem domain. If you look at a specific point p x y, the solution at this point depends on whatever happens anywhere in the domain. So if you introduce a small disturbance at any point at the boundary or inside the domain, anywhere, that influences the solution at our specified point p x y. Similarly, if you introduce a disturbance at p, its effect is felt everywhere. And in fact what we theoretically call here that the speed of propagation of disturbance, that speed is infinite. Now that introduces some complications here, since the solution at or disturbance at one point affects the solution everywhere. The solution of elliptic PD is relatively cumbersome, and in this case we must specify BCs must be specified along all the boundaries. Okay, so now this is general description about the nature of the PDEs, or what we call quasi-linear PDEs. We have had a look at some of the examples. Now can we extend this classification to our flow problems? So we would be primarily solving Navier-Stokes equation and energy equation. So what is the nature of Navier-Stokes equations or energy equations? So, classification of Navier-Stokes and energy equation. There are broadly two cases which we would like to deal with. Let us first take the case of incompressible flows, where the situation is rather simple. So, incompressible flows, if the problem is time dependent, unsteady case, so the nature of equation is what we call parabolic in time, because we have got a first order derivative in time, and elliptic in space. Now, this elliptic in space, this nature comes because of the presence of second derivative with respect to x on the right hand side of both Navier-Stokes and energy equations, and the consequence is that we require one set of initial conditions at t is equal to 0 and boundary conditions specified everywhere on CV boundary for t greater than 0. For a steady case, the nature of both of these equations, Navier-Stokes as well as energy equation, it is elliptic. So, we only require here bases on the domain boundaries. Next, let us move to compressible flows. Now, in the case of compressible flows, the life is bit difficult. The nature of equations is what we will call mixed. And in fact, it would depend on a non-dimensional number called Mach number. So, depends on local Mach number, and because it's local Mach number, we can make certain observations. That is, first, if Mach number ma, if ma is less than 1 everywhere, this is so typical of what we call a subsonic flow. Okay. Now, in this case, nature is similar to that of equations for incompressible flow. Okay. Now, if Mach number is greater than 1 everywhere, that means our flow equations, both momentum as well as energy equations, they would have what we call hyperbolic nature. Otherwise, we will have mixed nature. Similar type of classifications we can extend in the case of Euler equation, and for details we will have a look at few of the references to which you can have a look at, that how do we classify energy, so Euler equation and full potential equations. And next we will have a brief look at our boundary conditions before we close this module. So, let us see governing equations which we had, continuity, momentum or energy equation, they would be the same irrespective of our problem domain. then what makes each problem unique? That uniqueness is imposed by what we call boundary conditions, which act as the constraints and establish the uniqueness of the flow field for a specified problem. Now in normal flow simulations we will encounter two type of boundary conditions. The first situation would be that, look, we have got certain physical boundary conditions, we have got physical boundaries which are actually present there, and we can say that the constraints which are imposed by these physical processes happening at bounding surfaces, so we will call these things as physical boundary conditions. The second case would be artificial boundary conditions which are specified at the boundaries of computational domain, which are not natural boundaries. To understand the second aspect, let us have a look at an unconfined flow around a bluff body. So unconfined flow, or it could be a car, we want to simulate the flow around a car. Now in this case, how do we specify our problem domain? The car is moving in an unconfined air, so we cannot take this infinite domain in our numerical solution. So we have to somewhere break or put what we call artificial boundaries, and by putting these artificial boundaries we introduce what we call artificial surfaces, and we have to specify what would be reasonable boundary conditions at these artificial boundaries. So these are artificial boundaries, and of course in this case we can also have a set of physical boundaries, that is car surface and our road surface. So these are our physical boundaries. Now for our typical boundaries, which conditions we can find for viscous flows at physical boundaries, that is, say if you are dealing with a flow surface or solid surface. So since the flow is viscous, the velocity of the flow would be same as that of the solid wall. So we have got to impose what we call no slip boundary conditions, which is given by V is equal to Vw, where Vw tells us the velocity of this solid surface. In majority of applications Vw would simply be 0. For energy equation we have to specify the wall temperature, that depends on our physical processes which are happening. Maybe in some cases the solid surface has got a constant wall temperature, so in that case we will put T is equal to Tw, or we would have a specified heat flux, that is Q is equal to Qw. So these would be typical conditions for viscous flows. If you are dealing with inviscid flows, then by inviscid means there is no viscosity present, so there could be a slip between the solid surface and the fluid, but one thing is very sure, that the fluid cannot penetrate a solid surface. So we will impose what we call slip condition Vn, n stands for the normal velocity, velocity component normal to the surface, so Vn is equal to 0. Rest these two conditions, one of these two conditions have to be specified for energy equation, that is specified wall temperature or specified heat flux. The only difference in the case of inviscid flow would be that in the case of velocity, that is we have to impose what we call a slip condition by setting the normal component of velocity as 0. What other boundary conditions we encounter? We have what we call inlet boundary. Now the inlet boundary condition could be at both physical as well as artificial boundary condition. We have got outflow boundary conditions, symmetry boundary condition, periodic boundary conditions, and so on. There are a variety of these types. Now some of these we can have a brief look here. For instance, let's get back to our example of this simulation of flow around the car. At upstream end we have got to specify the velocity everywhere. So this would become what we will call as our inlet boundary or inlet boundary condition. So u has to be specified as a function of, or the velocity has to be specified as a function of spatial coordinates and time. What happens at this top artificial surface? We would say that the flow or temperature does not vary across this surface, so we can impose what we call a symmetry condition here at the top, that is for any flow variable del phi by del n that is equal to 0. There is no variation of a given quantity, or phi could be any velocity component or it could be temperature, it does not vary along the normal direction. Similarly, on the downward side we can specify what we call outflow boundary condition. So we have to specify pressure, and we can say that look, there is no variation in the velocity components along the outflow direction. So that completes our outflow boundary condition. For further details about these boundary conditions and mathematical classification, you are encouraged to read these few very nice books. This Computational Fluid Dynamics by Anderson and Computational Methods for Fluid Dynamics by Fertziger, and the Introduction to Computational Fluid Dynamics by Versteeg and Malala-Sekara. Each of these three books, they give some description about the derivation of governing equations. They contain in very nice detail about classification procedure, and they also have they are generally useful as a textbook for numerical schemes which you are going to learn later on. So that is where we are going to now put a full stop to this module, and in the next module we will start off with finite difference methods.